Koss. I'm a blacksmith and fabricator with an interest in armor since 2008.
I'm Patrick Thaden, metalsmith who began working in metal and fabrication and armor reproduction work in '97.
Our project is about fabrication techniques used in making one-piece helmets in Europe between the 12th and 16th centuries. Most academic sources so far have had very little to say about specific fabrication techniques, um, and those who have made more specific arguments have missed certain foundational techniques. Our goal is to correct this and to suggest a specific evidence-based production process with a focus on the quote unquote missing technique, which we call stretch raising. We compare our results to extant examples, both in interior texture and tool marks, as well as thickness distribution. So just a little background about us and our project. I started making armor in 2008, learning mostly modern techniques, and then gradually focusing more on historical accuracy, first in form and then eventually more in technique. I learned from a lot of old timers in the armor community, many of whom had experience both in handling originals and in making reproductions. Wade Allen, Robert McPherson, James Gillespie, to name a few. They introduced me to the concepts and arguments behind stretch raising, and I started experimenting with the process in 2014. This is when I made contact with Patrick and saw his previous research and experiments.
So, for me, a little background while I was traveling in Europe back in '97, I was introduced to a man that was making modern medieval styled armor. I began working with him while I continued my adventures around Europe. I began focusing my travels to allow me to see and handle historic pieces of armor. I've now been to over 30 museums, from small privately held displays to the largest European armor collections in the world, and have now handled hundreds of authentic pieces. As I had these opportunities, I began seeing vast differences between the originals and their modern counterparts. There have been many published works discussing armor, but they mostly focus on the form, types, and origins of armor rather than any real information on how it was being made. This is what intrigued me the most. Modern wisdom relied on sheet metal, and most modern armorers at the time were using a process called dishing or sinking to make helmets. Sinking is the process of creating a volumetric form through hammering a sheet of metal into a negative form or void. This tends to stretch the inner area of the material, which limits the depth of the raised piece and does not allow for a helmet depth object to be made in one piece. In my search for understanding, I began thinking one might need to start with thicker material so as not to overly thin the center. This, however, would leave an extremely thick-edged and heavy piece and not be representative of the originals. In 1998, I came across an article written by Jason Grimes, who was theorizing that a helmet depth piece could be achieved by thinning the edges of a plate first and then stretching the center, which would allow for a more uniform thickness final piece. Over the next few years, I began playing with this idea as well as continued my research into different techniques and began seeing modern metalsmiths using a process called angle raising. This is a process of creating a volumetric form by hammering a sheet of metal over a rigid form in a series of concentric courses, starting from the center and working toward the outer edge. I became fairly proficient in this technique, but it wasn't giving the same look and feel as the original pieces of armor. I continued looking into other techniques and began finding various groups of smiths that were using a technique I felt might be more applicable. In 2004, I bought two videos. One was of coppersmiths in Santa Clara del Cobre. They were some of the first I had seen that really showed a technique that I felt could be applied based on the technology available to early armorers. The other video was shot in the 1970s and showed a small town in northern Italy called Bieno, where metalworkers in a 17th century hammer mill were making iron buckets 7 at a time from heavy plates. This was exceptionally exciting because they were working with iron in a region that was a major armor production center in the 12th to 16th centuries, and using the same techniques as the Santa Clara coppersmiths. With further research, I found people in Thailand, Bali, Nepal, Japan, all using a similar technique of starting from thick materials rather than rolled sheet. This excitement renewed my interest, and I began experimenting with the techniques I was seeing used, but being a one-man shop, this was difficult and I was only able to attempt a few limited experiments. Though promising, it didn't get to a level I was confident in being able to share widely.
So far, angle raising is still the most common method used to create deep forms across Europe and the US, and it's still largely thought to be the main method used to fabricate one-piece helmets in the medieval period. As far as I know, Nicholas Duprass was the first person to argue for specific fabrication techniques in an academic context. In his 2012 PhD thesis, he argued explicitly that deep helmets must have been made by angle raising from sheet metal. The issue, of course, with sheet metal is one of the main starting points that leads us into our current project. Thinking backwards from a medieval perspective, we know that medieval iron and steel production involved both direct and indirect smelting methods. Regardless of which smelting and refining methods specifically were used, and the details of this seem to be an open question, slightly tangential, but in either case, the starting material would end up consolidated into a large, thick billet. We found experimentally that forging sheet metal from thick stock without a rolling mill is very difficult. A rolling mill produces sheet only as wide as the rollers. This allows metal being forged to flow unconstrained in the direction of rolling. However, if you're trying to forge a sheet using dies which are much shorter than the width of your sheet, this creates a problem. Metal near the edges of the plate is free to expand outwards, but the metal in the center plate tends to be constrained by the surrounding material and has nowhere to go except out of the plane of the sheet, which creates volume. On thick material, this is less of an issue, since the thickness allows the metal to upset a little bit, which kind of allows the metal to flow out of the center towards the edges. The thinner you get, the less this works in practice. In our experience, this really seems to change around the 3 millimeter mark. This problem gets much worse the bigger the sheet you're trying to make. I've made some smaller sheets for a type of helmet assembled from panels called a Spangenhelm. This style is earlier than the period we're looking at, but it was useful to give us some perspective on the transition from multi-piece helmets to one-piece helmets. Forging the small plates required for this style was difficult, but not too bad. I certainly would not want to try and go bigger. Since stretch raising doesn't require sheet metal as a starting point, it sidesteps this problem entirely. In effect, rather than forging out a sheet and then shaping that into a volume, stretch raising accomplishes both of these tasks at the same time. The process starts with a rough billet. It's relatively simple to forge this down into a thick plate. We've found that about 10 to 13 millimeters works well, which is what we've shown here. From there, you simply thin the edges out, which are free to expand outwards. The thickness distribution of the starting flat plate becomes a kind of roadmap for the finished depth of the vessel. Once the thickness distribution is in place, stretch raising begins in earnest. This involves simply hammering the metal directly against the flat of the anvil with small face, long neck hammers. This is us, by the way, our experiments. And since the metal is constrained by the surrounding plate, the pinched metal has nowhere to go except to expand outwards and into depth. Working around systematically in this way, you can transform thickness into depth. The texture left by these heavy blows from the inside strongly resembles what we see in medieval examples. This is the original on the left and then ours on the right. Stretch raising works best to create the raw volume. Once the rough volume has been created, it can be worked to the final shape using angle raising. This tends to smooth the inside texture. Here you can see, you got to switch slides there. Here you can see a lower edge of an original piece taken side by side with one of our experimental pieces. The angle raising can also create compression lines, which again, we can see here compared with the original and with our experimental version. Practical experiments and thickness data. One of the bits of evidence that points us towards this technique is thickness distribution of the original pieces. The thickness of one-piece helmets can vary quite dramatically, with thick and thin spots placed apparently at random. This matches with our experience. Over the course of dozens of vessels forged in this manner, we found it quite difficult to avoid the issue of having local thick and thin spots. When we take a set of measurements from a given helmet and compare the extreme ends of our results with the average, we find that our stretch raise experiments vary quite widely, matching similar data pulled off extant examples. Our test pieces that were angle raised from modern rolled sheet have some thickness variation, but it's much less extreme and less random than the stretch raised versions. However, our experiments in forging simple plate for the Spangenhelm have also produced very uneven results. This suggests that somewhat crudely made plates, which were then angle raised entirely to shape, could plausibly produce some fairly significant thickness variation, making this metric a little bit ambiguous for our purposes. It's also possible that a more thorough and systematic method of taking thickness measurements could shed further light on this. However, if we look outside of helmets at breastplates, the thickness data is more revealing. While breastplates tend to show extreme and somewhat random thickness variation, they're typically thicker at the center and tend to thin towards the outer edges, at least on average. This suggests a starting piece that's had its edges thin and its center left thick. The interior marks are also consistent with heavy hammer blows from the inside. More thickness data would help out greatly, but it can be difficult to gather. For our projects, we use some purpose-made calipers. Mine is a relatively crude but effective homemade pair, and Patrick's is a highly developed set. Based on our current experiments and the evidence available, we feel that our proposed technique is pretty plausible. Beyond the basic arguments, there are some other interesting aspects of the discussion that we've looked into. We've done some experiments with forging modern puddled wrought iron into helmets, with the understanding that it's a little bit closer in working properties to medieval iron and steel. From the start, we suspected that stretch raising would be more viable than most modern techniques when working with a slaggy starting material, especially sinking is fairly ineffective on slaggy material. And that seems to generally be the case, but we need to explore this more. We've started some preliminary work on experiments with bloom iron. Bloom smelting has been a fairly large diversion, and we've really just scratched the surface of that.
One of the other areas we've experimented with were following the Smiths in Bienno. They were actually stretch raising 7 plates at one time. We have done 7 different stack raised experiments between the two of us, and some of the exciting things found were the ability to spend more time hammering as it retained heat longer. Another was the fact that as the plates are separated, it was discovered that the plates lost no material due to oxidation, saving material in the process. We have done these stacks with sledgehammers and found the time to achieve a good depth took no more time than doing a single piece.
So that's about where we're at right now. We're working on compiling what we have into a more coherent form, while also trying to collect more thickness data and photos of originals, all with an eye on writing a paper or two. We're looking to get a bit of an outside perspective and feedback on our general direction and approach. Anyway, thanks for listening, and we'd be happy to answer any questions.